Good evening, everyone, once again. My name is Aveen Dayal. I'm a PMRF PhD student at IIT Hyderabad, and I will be your TA for this course, for this live session for the course Deep Learning for Computer Vision, conducted by Professor Vineet and Balasubramaniam. A little bit brief introduction about myself since it's the first class. So, I'm a final year PhD student, and my research area is basically building robust deep learning models for uh, computer vision techniques and computer vision area, and also multimodal areas. And apart from that, I think these live sessions basically to give an introduction, so it'll help you understand the course better apart from what the lecture videos which you have seen provided by the professor in the SWIAM portal. So these will help you understand how to solve the problems, and also at the same time, understand any other coding skills or etc. whatever that will be required for you to do this course easily. So that being said, let's keep this a little bit informal. We don't have to keep it very formal. So the pattern or the way we conduct these live sessions is that we have some questions with us, like around 8 to 10 questions every week. And so these are questions that can you can solve with the help of pen and paper that I will show on the screen and we can discuss. So and after that we'll have some code walkthroughs, which mostly based on the techniques and algorithms which you see during the lectures. Yeah. So let me just share my screen and we can get started. So if you have any questions during the session, you don't have to wait till the end. You can always post your questions in the chat. I have like multiple screens so I can answer your questions while during the session too. Don't have to wait till the end. Like I said, let's keep it informal, but don't unmute yourself in between because it's a big class. Sometimes it'll cause unnecessary noise for other people. Okay. So let's start with the first question. So, like I said, I'll go through by discussing questions and the concepts, all both of them together. So, this is a very simple question. So, you must have gone through the lecture videos which professor has posted, and in that, the very first question you ask about in computer vision is what are the different ways in which you can represent image format, coloring format, basically. So, these are the five options in front of you. So, what do you think are the correct possible coloring formats from all of these five? So, there are more than one correct answers. So, whatever you feel is the correct, you can just go ahead and post it in the chat. Maybe I'll just give a quick 1 2 second pause so that you can just look through it and you can post your answers in the chat. Any guesses? So, I'm assuming everyone knows the basic. Yeah, like someone posted A RGB. RGB is definitely correct. Other than that, there are some more correct answers too. Okay, I think there are a bunch of answers. So let me discuss the answers itself. So the correct answers are A, B, C, D. Now let's go ahead and discuss what are these correct formats for everyone who are not aware of other formats other than RGB. So the first one, I think everyone is aware, RGB, the basic red, green, blue structure, which any digital image, whichever image you click to your iPhone, like smartphones and all, those all usually are represented using red, green, and blue channels. That is a standard format. Apart from that, there is a other very popular format called RGBA, where RGB stands for the same red, green, blue. A is the alpha parameter, which is usually the transparency. So transparency channels are usually helpful when you're clicking more digital images like movified or in cinemas or in other use cases where this particular transparency gives a more see-through type of a feel of that particular image. So this is again a valid image format. Coming to CMYK, this is not very popular for general crowd, but this is very popular amongst people who use color printing. So usually, the color channels are represented in such a way that whatever colors are absorbed by the image, those is what is represented. Like RGB, because red, green, and blue are usually absorbed by the image, whereas CMYK is the opposite. It is the absence of whatever is the missing colors in the image. So CMYK stands for cyan, magenta, yellow, and key or black. So this is like the absence of the light. Whatever is not absorbed, that is what you represent using CMYK. Again, like I said, popular amongst printing processes, not very much in general usages. Then comes hexadecimal. So people who are familiar with web development or poster generation, etc., you must be aware of these hexadecimal formats. So this is a six-digit representation using hexadecimal numbers. So we all know that decimal runs from 0 to 9 with at the 10 digits. Hexadecimal goes from 0 to 15. So it's the same 0 to 15 numbers. In how do you represent after 9? You use certain letters. That is why you see here the last example, right? Hashtag FFFFF. So that is a way of representing one particular color in hexadecimal. This particular FFFF represents white. Similarly, you have something for black also, which is all zeros. So this is another popular format. The last option which was there, RBX, there's nothing, there's no format for RBX. That's wrong. And apart from that, maybe let's discuss what how you can represent an image, since it's a very good way, since we're already discussing about coloring formats. So what is a image typically? So we all are familiar with matrices, right? So let's say I have a matrix. Let's call this matrix X. Now, what does a matrix have? Usually, a matrix is typically accompanied by the dimension or the size of it. And that is nothing but M cross N I'm writing over here. So this is a simple 2D matrix. Now let's say we want to complicate stuff, which is usually the case. We want to add more and more dimensions to it. And we keep on adding like M and let's say K. We can add like n number of dimensions. Like there's no limit to it. Let's simply call this a three-dimensional. Uh, this is called a tensor usually. It's anything more than two dimensions, we call it a tensor. So this is a three-dimensional tensor. Now, what does matrices have to do with images? Like, you must be knowing that any image can also be represented by these three dimensions, where M and N are usually your width and height, or you also call it resolution. And K is nothing but your channels. In our simplest case, we use three channels, RGB, or you can use more number of channels also. So here, each particular element in this matrix is nothing but a pixel. That is what is used in modern digital images. So let's say this, what is this pixel? This pixel is nothing but a integer value usually, and this integer pixel lies in the range of 0 to 255. So a typical image, if what's say you call it high definition images nowadays, right? Like something like uh, 2048 cross 2048. That's a pretty decent resolution image. So it's nothing but matrix you can imagine of three channels, and each element is nothing but a pixel. And pixel is nothing but it can have a value, integer value between 0 to 255. Now, sometimes people also say ki we can normalize this particular image instead of having 0 to 255. We can always normalize it and represent it as 0 to 1. Standard normalization process. There's nothing unique about it over here. But why do we need 0 to 1? Maybe it might be very no, unclear at this stage. But when you go ahead in the future lectures, especially when we start talking about neural networks and all, we always convert 0 to 255 into 0 to 1. That because the training process becomes much easier. So for now, people who are familiar with scaling and feature scaling, they will quickly relate to it. If you don't worry. We'll discuss it in detail when we come to neural networks. Okay, so this is one way to represent a typical image. Is there any other way which you must have gone through the lectures? You can post your answers in the chat. Any other way that we can represent this typical digital image? Let's take a wild guess, like in the lectures also. This is a very standard way of representing images, but this is not the only way to represent images. Any other way? Exactly. Like people have posted in the chat, as Akhil has pointed out, functions. Functions are a very interesting way to represent images. and also signals. That's also true. But we don't usually encounter that because it's not very intuitive for us to understand. I'll show you some examples in today's lecture by the end of it, how the functions of a typical digital image which you see can also be represented as functions. Again, not very intuitive to see, but it is also one way to represent. Okay, that's great. Let's move on to the second question. So this is a little bit involved. Maybe if you have pen and paper from wherever you're watching the lecture, you can do it and tell me. So the question is, let's assume you have an image of size 2n cross 2m, and you have a patch operator of size p cross p. There are certain conditions about p and m such that minimum of n comma p is greater than or equal to p greater than or equal to 1. Then how many different patch operations does the value of the cell n comma n contribute? I hope this is clear. If you want, I can repeat the question once again. Let's say we have an image of size 2n comma 2m, and we have a patch of size p comma p, and we want to identify how many different patch operations as the value of the cell n comma n contribute. So someone has already posted certain answers. Maybe let me just quickly wait for a few seconds until everyone can try it out. Okay, maybe in the interest of time, let me go ahead and explain the answer. So the correct answer is D, which is P cross P. Let's see how that is happening step by step. So what is the question? Let's draw it and see. It's saying that, sorry, it says that, it says that we have an image of size 2n cross 2m. It also says that we have a patch operator, which means something like this. Sorry, let's keep it square because it's a square patch. Size p cross p. And the question is, this p cross p, what does a patch operator usually do? It basically slides, right? It slides on this input image 2n cross 2m, and it calculates some output answer. That is what usually patch operators do. But that's what you will see correlation or convolution, which we'll discuss later. But typically, patch operators do this. Now, what is the question? It says that let's say we have a particular pixel, which is n comma m. How many operations this particular pixel is involved in when this patch operation is sliding over the image? So that is what the question is asking. So ideally, let's start writing out what are the conditions. First condition is, what are the possible n values? Okay, the possible n value goes from 1 to 2. Oh, sorry. What are the possible I values, not n values? My bad. I values go from 1 to 2n minus p plus 1. So this is the possible I value. Similarly, j values. I and j is nothing but you can think it's like an iterator. Any point, any pixel in this value can be represented by I comma j. So I goes from this, and similarly, j also goes from 2m minus p plus 1. Now, if I want a particular pixel n comma m to fall in that operator patch p cross p, what should be the condition? We ideally want n, I'm writing it on the bottom, to lie between I to I minus p plus 1. This is what we typically want. Similarly, for m also, we have this condition. Plus 1. what does this condition even mean? Let's again draw and see what does it even mean. So this is the original image. Let me take some other color. This is a patch. Now let's say if n comma n can either lie here or anywhere in this patch of p cross p. So this basically, this condition which you see, the first condition, it's across the rows, you can say. So this n value can be from the leftmost, it can go to the rightmost, and that is what this particular equation relationship is capturing. So this is why this condition is coming, that it could be anything. And what is this size? The size is nothing but p. That is why you get that I minus p plus 1. So this is how the equation comes through. And if you rewrite this equation, this is what you get over here, which is shown over here in the slide. N minus p plus 1 less than or equal to I less than or equal to m n. Similarly for j also you have this condition. Now what are all the possible values for each of them separately? For the first one, how many values can I take? P values, right? So you're going from n minus p plus 1 to n. So you like, it'll be like n minus p plus 1, then n minus p, then n minus p plus 2, n minus p plus 3, so and so, so and so, so and so. It keeps on going. So there are p values. Similarly, for the bottom one also, same idea, you'll have p values. And totally, how many values you're covering? P into p. That's why you have p square values. Yes, sorry. Like someone has pointed out, it's less than equal to, my bad. Everything will be less than equal. Thank you for pointing it out. It's less than or equal. Let me quickly pause for a second. Any questions, anything that is not clear, I can repeat again. Or if it's clear, we can go ahead. Okay, Jeff. Then let's move ahead if there are no questions. At any point, again, since it's the first class, I'm reiterating myself. Any questions, any doubts, please, you can ask me again. I think someone has a question. Can you? Okay. So let me read. Let me restate the question. So the question over here is: let's say you have a image of size 2n comma 2m, and you have a patch of size p cross p, and there are some conditions between these variables of minimum of n comma n greater than or equal to p greater than or equal to 1. Now the question is: let's say a cell n comma n, how many times will this cell participate in the patch operation? So so uh, so to understand, I think there's a question: which assignment is this? So, uh, for the person who posted in the chat, so this is not from any of your actual assignments to solve. So these are problems which will be similar to your assignment problem. So by me solving these problems, it will help you understand the concepts better, and you can solve your actual assignments problem. So that is what the intention or the goal of these live sessions is, to help you solve your actual assignments problem. So these are not from any assignment or anything. Okay. So coming back to the question. So what is the patch operator? What does a patch operator even mean? So let's first talk about that. Like I said, there is an image I. We typically have a small patch, which is, let's call it capital P. Now patch operator is nothing but it tries to slide on top of this image. Like it will be, this is one time it will get, and this will result in an output O, 1. Similarly, it now moves one cell ahead, one column ahead, and this will result in output 2. And this is how typically a patch operator does its particular operation. Now, what the particular question is saying is, let's say this cell, there'll be an n comma m cell, right? This is the centermost cell, that is n comma m. Now, when you're doing this patch operation, that is sliding, taking this p and sliding one column at a time, moving to the right and then moving one row at a time below. How many times this particular n comma n will be involved in this particular patch operation? Now, if you zoom in, let's try to zoom in. So let's say this is one patch. Now, where all n comma n cell can be? It can be here, or all the way till here. It can also be all the way down and all the way to the cornermost, right? So this is what we're calculating. These all dots which I'm keeping, right, in between all the dots. What is this value total? So that is how do we solve that? That is where these equations are coming. So first, topmost equation which you see, this equation, this is nothing but a standard boundary itself of what I and j can be. I and j is nothing but that each cell value from one cell to another when we go, right? What is that cell value? That is what I comma j is. And first topmost condition is nothing but a simple boundary condition. The actual when we are equating how many of these n comma n lies in that patch, that is what the below ones show. And if you rewrite the below conditions with as seen on this slide, this is what the rewritten conditions look like. And what is the particular I and j values in these conditions? P for I, P for j. So the total is P into P, P square. So I hope this is clear. Any doubts in this? Okay. And let's move ahead. Now let's take another question where we are saying that let A be a 2n cross 2n matrix and B be another matrix of size 2p cross 2p. And we are saying that P is less than or equal to n, greater than or equal to 2. Now suppose A is a skew symmetric matrix and B is a symmetric matrix. And we are saying let C is equal to B convolution of A. What is the sum of all the elements of C? Maybe to make it simple, let me also give you a hint. I'll tell you skew symmetric matrix is nothing but A transpose is equals to minus A. A symmetric matrix is nothing but B transpose is equals to B. Now with this hint, try to solve this question. I'll wait for a minute. You can just post your answers in the chat. Okay, we got some answer n minus p. Anusha, that is not correct. Maybe just rethink once again based on the properties. Yes, Pooja has posted option C. That is correct. So maybe in the interest of time, let me explain. So the correct answer is 0, which is option C. So let's maybe let me go back to the question. Let's see what the question is saying. You know, A is certain size matrix, B is certain size matrix, B is smaller than A. That is what is given in the condition. Then we are saying that A is a skew symmetric matrix. For people who don't know what is a skew symmetric, this is the property. A transpose is equals to minus A. To understand the good thing about this property, when you say A transpose is equal to minus A, it means that all the diagonal elements of A will be 0. And let's say if this is A, this will be minus A over here. Similarly, if there's an element B, there'll be an element minus B. C, minus C, and so on for everything. This is how a typical skew symmetric matrix look like. Now, with the same logic, B transpose B also has a certain pattern where there will diagonal elements can be anything. It could be, for now, I'm just keeping X. So it could be anything. But here you'll have the same pattern. A will be A, B will be B. So this is another way of looking at B transpose B, which is a symmetric matrix. Now, with these things as clear, do we have to do? We have to do convolution. Convolution is nothing but it's element-wise multiplication and addition of when you do the patch operator of B on top of A, right? So maybe let's diagrammatically see what convolution is. So if this is A and we have a patch operator B, so what we do for convolution usually, we first, so if I want to do convolution, that operator is a star. So we first flip B. So in this case, flipping doesn't matter because it's a symmetric matrix. So if you flip, you don't, that doesn't matter over here even if you don't flip because it's a symmetric matrix. But ideally what we basically want this capital A, this B to slide on capital B. And what is the operation? So let me write it clearly. So this operation is nothing but element wise multiplication and element wise addition. Now let's zoom in. Since it's the first class, I won't assume anything. Let's zoom in what this is happening over here for one particular patch operator. Now let's say I'm taking some dummy numbers to be clear. We'll use different colors too. Let's say I have x1, x2, x3, x4. Could be a bunch of other values also. This is A. Now let's say B is a patch operator. Now B inherently has four. It should have four values, right? We are calling it B1, B2, B3, B4. Those four values are placed on the top of the A. So what does convolution basically give us? Convolution basically gives us x1 b1 plus x2 b2 plus x3 b3 plus x4 b4. This is one particular operation, a patch operator, when b is convolved on top of a. And so here b is after flipping. Okay, this b1, b2, b3, b4 after flipping. For now, I'm ignoring because in our particular it's a symmetric matrix, so don't worry about the flip. Now, if you look at it, since A is a skew symmetric matrix, sum of all the elements of A is zero. That is what this particular, which you see, right? That's what I wrote over here. Skew symmetric matrix has this property: the sum of all the elements is zero. So then what we're looking over here is nothing but it's like a weighted sum of sorts. So the patchwise operator, it's not whenever you do it across the entire matrix, say it's a sort of weighted blockwise summation which you're doing. And this total sum of all the elements of the A is zero, and intermediate blocks when you take separately and you add them up, that will also come to zero. So that is why when you do this entire convolution with this skew symmetric matrix with the patch operator as symmetric, the answer will be zero. Is this clear? Any doubts or anything that is unclear? So I hope you all watched the initial lectures of what is convolution and cross correlation. If not, I would highly encourage you guys to go back and read those. Without that, understanding this will be harder because the idea of this tutorials or live sessions is to help you on top of what you already watched the lectures. I can't start again and repeat the same content what professor has said. I'm happy to answer the questions if you have regarding those particular content, but I highly encourage you to watch those lectures and then come to these live sessions. Any questions or any doubts in this question three? Okay. So if not, let's move ahead. Question four. There's the same explanation. You can, so yeah, all these contents along with the recorded tutorials which will be uploaded. So all of these you'll get after this session also. So you can you look at it, all the explanations in your own. That is also possible. Okay. Now the question number four. So given this particular kernel, A is equals to this particular 3 by 3 matrix, is this kernel separable? And also, what are the singular values? Maybe let's forget about the second part. What are the maybe let's ignore the second. It will take some more time to calculate. Let's focus on the first part of the question. Is K kernel separable or not? It's a simple yes or no question. I'll maybe quickly wait for a minute before you solve this. Please post it, your answers in the chat as usual. As someone has rightly posted, I think it's Ahana. Ahana is correct. The answer is no, it's not a separable matrix. So let's maybe take a step back. Let's understand what is separability, what is non-separability. Okay, so first, before even understanding separability, let's talk about matrix decomposition. Maybe for people who are not familiar with linear algebra, who are still figuring it out, maybe let me give a very high brief overview. And you can always look into other resources online to better understand this. So any typical matrix K can be decomposed. Any typical matrix K can be decomposed into this matrix, three different matrices, U, sigma, and V transpose. So this is called as SVD decomposition. So this is a very powerful algorithm or technique, you can say, which is there in linear algebra. It basically says that any matrix K can be decomposed into smaller matrices, not smaller, into separate matrices like U, sigma, and V. So there are terms for these matrices U and V and sigma. For now, you can just call them U, sigma, and V. Now, if you expand this matrix in terms of its element wise multiplication and addition, that's where you see the summation term right side. So you have the sigma matrix is nothing but a diagonal matrix. So sigma is usually has only this structure, sigma 1 to sigma n, or everything else is 0. So that is how a typical structure of sigma matrix is. U and V can be anything. So when you expand this matrix multiplication in terms of element-wise summation and addition, this is what you see on the right side, which I'm highlighting right now. So this is very interesting to understand separability, because if let's say sigma had more than one non-zero value, so then when I'm expanding, it will be something like, let's say I have sigma as two values, both of them are non-zero. It will be sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose. Okay. But this you can quickly say this is not separable. Separability means you can literally take K and use two different vectors to make that K. But here you're not having two vectors, right? You have four vectors. You need to know what U1 V1 is, you need to know what U2 V2 is. But let's say there is a situation where this sigma matrix had only one non-zero value and remaining all zero values. So then what will be the situation? It will just be sigma 1 U1 V1 transpose. Everything else will be zero. Now, in such a situation, we can say that this particular kernel or matrix K is separable, because you can write this K in terms of just two vectors, U1, V1. So this is what you need to understand to know whether it's separable or not. And these sigmas are usually called as singular values. So you ideally calculate the singular values of this particular matrix K. There's a standard formula to calculating that. And then, so I'm not sure that formula is also mentioned in the slides. You can look into that formula in the lecture videos. So that particular formula using which you can calculate how many non-zero singular values are there. If there is more than one, you can quickly conclude the statement that it is not a separable matrix. So this is why we are saying this particular K is not a separable matrix, because it has three non-singular values. Is this clear or any doubts? So again, don't worry too much about singular values and all. For now, you can just understand what this formula represents. If you understanding what is happening in this, it's good enough for now. We'll see the advantages. Uh, we see this advantages of separable matrix in the next few questions down the line. Why do we even need separable matrix? What is the advantage of such matrices? We can see later. So there is a question: more than one for any matrix. Uh, I didn't get more than one. You mean, yeah? If for any matrix, if there is more than one non-zero singular value, then matrix is not separable. So basically, what I'm saying is, if there are like sigma I, the bunch of sigma i's where I can go from 1 to n. Okay. In this all sigma i's, I want only one sigma I to be non-zero. Then it is a separable matrix. Remaining all should be zero. I hope that is clear. Okay, let me go ahead. Now, let's go to the simple question. I hope I already explained what convolution is, but let's do it again. So you just have to compute the convolution of the following two sequences, convolution of A and B, remember to use padding. So basically, to keep it simple, let's say this is B is the bigger matrix, A is the patch operator, and you have to do convolution. Remember to use padding to so that the size of B does not change. Here it's not a matrix, here it's just single one-dimensional vector. I think you get the idea. So post your answers in the chat. I'll just wait for a minute. Any guesses are also fine. You don't have to calculate all the values. Just try it out. Maybe you'll then get some questions and then we can discuss. In the interest of time, let me just explain this particular answer. So, for people who already tried it, maybe this is the final answer. It's 1 minus 1 minus 1, 3, 6 minus 2 minus 6. Let's see how do we solve this. So first things first, let's understand what is even padding. Because up till now, before I explain what is a convolution, convolution is nothing but you have a particular patch. In this case, patch is A. You have an input which is B. Let's keep it simple. And first, what you have to do, we have to first flip the patch. So original patch, you basically flip, I think 180 degrees you can call it. And then once you flip that, you then do element wise multiplication and addition by keeping that flip patch on top of B and sliding one column to the right. And once you finish the columns, you come one row to the bottom. So typically when you do this, so the output of a convolution, let's say this entire process, we call it convolution operation. So the output of it will usually the size, let's call it, maybe let's call this matrix O. The size of O, size of O is less than size of B, initial input. This is how usually convolution operator happens. It reduces the dimensions of the original input by certain value. Now, sometimes it is okay. Sometimes we are fine with reduction, and sometimes it is actually helpful in reducing. You will see in your later lectures in this course that we want the convolution to keep on reducing the size of the input matrix. But sometimes it is not okay. Sometimes we want to keep the size of the input and output to be the same. Now, how do we do that? Because convolution, the way the operation is defined is you will do any, you're basically kind of aggregating all the values which are there in this patch and then giving one element, right? So you're ideally reducing the size. To avoid this, people have come up with strategy called as padding. So typically, you padding means you basically add some extra values on top of it, and also on the side of it, like completely on this side also. Similarly, on the bottom of it also. On the bottom of on all sides of your original image or input B, you basically add some extra values. How many you should add, that depends on what level like what is the input output size you are getting. So that many, usually it will be like one extra column on the top, on the left, right, one extra row on the top and one extra row on the bottom. So in effect you'll add like two extra columns, two extra rows. That is typically what you add, but again it depends completely on your size of the patch operator A, the input size B. So there is a separate formula which we will discuss in later lectures for that. But imagine for now you have to add some padding values. So with this padding, now the patch will not start from the first element. So previously we started from here, right? This is what I'm highlighting. Previously we started from here. But now since we added extra, it'll actually start from the top row. So now you'll effectively save the size of the output in such a way that size of output after doing padding is equal to size of the input. When I'm saying size, it is nothing but the dimensions m cross n. Don't think of it as a number of values in pixel values. Just think of it as like m cross n should be same. So this is what typically padding helps with. Now, how do we do padding? If there are a bunch of options, maybe I will list down few of them. Padding can be zero padding. Very simple. Just add zero values, nothing else. In that all these blue things, you just add zero values. Then there is, I think, forgot the name. It's called, I think, wrapping or reflective padding. Uh, Wrapping or reflective padding, something like this. So what it basically does, yeah, mirror padding. Thank you, Bharathan. So sorry, it's called mirror padding. So mirror padding means basically you take these last row values and you mirror it over here of sorts. Uh, then there are a bunch of other options also, which you can, I think it's listed very well in the lecture notes. You can look into it. But the idea of any type of padding is to save the size. That's what the intent over here is. Okay, now let's come back to the actual question itself. Since it's are simple values, right? We can easily calculate over here. So we have like how many, what is the size of this? So this is like a vector of size 1 cross 5. Okay, and this is a vector of size 1 cross 3. If you ideally do convolution without any padding, think you will reduce two dimensions, you'll result into something as 1 cross 3. But we want to save the uh, original dimensions of B. So you add 1 0 over here. Basically, add two zeros in the start. So that is one way to do padding over here. So after adding two zeros to the sub, then maybe I'll write it in the next page. So effectively now B will become 0 0 and whatever the other values of B is. So now A will start from here. Since A is three values, right? So you start from here, then it goes here, and it keeps on doing until it reaches the end of B. And at each particular block blue, sorry, you do nothing but element wise multiplication plus element wise addition. Element wise multiplication plus element wise addition. Okay. Is this clear? Any doubts? Please don't hesitate from asking. I think please ask as many as questions as possible in this particular live session. This will help you understand better. Anything that is not clear, any idea of convolution is not clear, what is padding that is not clear. Uh, okay, that's a good catch actually. Yeah, I think maybe we don't have to add two zeros. Then 1 0 should be fine if you want the same level, same size as the input. So yeah, here we actually added two zeros, so we are getting bigger size. That should be fine. So usually padding, like I said, how much to pad, we'll give you a better formula once you start in the next classes with deep learning and neural networks. You'll have a very good formula where you can calculate the number of padding elements that you have to do. Okay, if there are no further questions, let's go ahead. So now let's talk about linear filters. Okay, so try to solve this question. Don't worry if you can't, we can discuss. This was already discussed, I think, similar question in the lectures also. But let's solve this again. So let's say I have this particular type of a filter or linear filter or operator, whatever you want to call it, patch operator, filter. All of these are the same thing. And what is this particular function doing? Given a particular pixel element m comma n, it will look at the intensity, that is nothing but the pixel value. And if it is greater than 100, if it will give a value of 255. If it is not, it will give a value of 0. So if you take this original picture on the bottom left, which is of Mona Lisa, and you pass it through this particular filter, you will get a black and white image. That is essentially what we're doing. Now the question is this particular filter G or this function G, is this a linear filter or not? So I hope you all remember what is the property of a linear filter. If you remember that, then you can pretty much easily solve this question. So again, I'll wait for a minute. Please post your answers in the chat. As Ullas Kumar has rightly posted, it is not a linear filter. That's correct. I'll just quickly go ahead because we have few more questions and code also. Yeah. So linearity is a condition is basically this particular condition which is on the topmost. Let me highlight it. This is the condition for linearity. So G, the function G of A plus B could be any two images, is equals to G of A plus G of B. Okay. Now let's see what do I mean by that. Let's say we have a particular image A at this location m comma n. For that A, we are having the value as 9. Similarly, let's for B, let the value be 20. You can take anything, doesn't matter. It should basically satisfy the conditions. That is what we're looking at. And if G of A comma n, what it will be since it is less than 90, it is 0. Similarly, G of B, which is because it is 20, which is less than 100, which is again 0. Now, if I do A plus B is nothing but 90 plus 20, which is total 110. Now, G of A plus B, which is over here, will be actually greater than 100. According to the function, the step function, if it's greater than 100, we should get 255. So we can quickly see that G of A plus B is not equal to G of A plus G of B. So this condition in the bottom, this is not satisfying this condition. That is why this particular filter is not linear. So very simple way to check linearity of any filters. Is this clear or any questions? This one, please let me know if there are any questions. I'll just move ahead in the interest of time for now. Let's see another interesting question. If your original image is this, if you have a convolution operator which is done using some filter h and your resulting output is this, what do you think this h should be? Some imagine what we are doing with convolution, we flip the kernel and everything. So just try to guess what could be. So if you think about it, we are like kind of zooming in on this left side, right? And we are shifting everything left pixel and kind of zooming inside of sorts. That is what is happening. So what should be that filter h that will result in this particular type of operation? You can take any guesses. We can just show you the filter. You can solve it by hand and you can figure it out. But any guesses for now? No, it's not average. We are not blurring anything. Averages are usually very. You'll see the average output to be a blurred image. Nothing is blurred over here. We're just literally shifting everything to the left. There's no blurring or anything. It's pretty much clear, right? Not clear in the same. Close. It's a two-dimensional matrix, Bharatan. You posted just a 1D vector, one-dimensional vector. But yeah, you're on the right track. So yes, everyone can try in your home at your own time. This is the that matrix which will result. There should be one at one place. Everything will be kind of zero. Maybe you can solve it in your own time and you can figure out how it is happening. But this is the final answer. But remember what we are doing, the convolution operation. That operation remains the same. That operation remains the same because it is nothing but convolution. As I said, let me recheck. What is this convolution operator? What do we do? Flip the kernel, which is filter or kernel, whatever it is. Flip h, then do element wise multiplication plus element wise addition. Okay, then let's go ahead. Let's look at this question. So maybe you can take some guesses. Everyone is aware of histogram equalization, which I think again was discussed. If not, I'll again discuss, but let's first try to answer this question. If you already watched the lectures, for people who have watched the lectures, if given these two images, left side is one image, let's call it image A, right side, let's call it image B. Given these two images, if you apply histogram equalization, will it always enhance these images or not? Maybe you can say yes or no for both. Try to understand what histogram equalization is doing. Okay, Pooja answered yes. So is it yes for both the images? Maybe you can mention like image A yes, image B yes or no. Let's think about it very clearly. There's a difference between the input images. Yes, I think Satish has pointed out. Yes, only the first images, actually, only first image gets enhanced. Second one doesn't. So let's look at it. Let's look at what the histogram equalization even do. So let's look at the graphs, and I'll explain histogram equalization through this only. So any particular image, like I said, it is nothing but a matrix, right? At the end of the day, a matrix of particular, in this case, I think it is approximately 600 in height and more than 1000 in width. That is what this dimension of images. And each particular element is nothing but a pixel value. And what is that element range, which we discussed in the first slide? Let's say this is one pixel, the range of it between 0 to 255. Now, what is this plot on the right side which you see? So this is nothing but the histogram of the intensity or image pixels, what do you want to call it, image intense pixels values of that image A. So there are histogram. I'm assuming everyone is aware of it. For people who are not aware, histogram you can simply think of it like a plot which calculates the frequency of a particular possible value. So on the x-axis, you have bunch of possible values for the pixel. It will go from 0 to 255. And then we calculate how many times how many pixels have value 0. So that is the frequency of pixel 0, right? So that is what we write over here. So in this case, 0. That is the value. Similarly, for pixel 50, how many such pixels have the pixel value as 50? Here in this particular case, if you draw a straight line, bear with me with that straight line, you'll get somewhere across more than 10,000, some to 12,000 pixel values have this pixel value as 50. So this is why uh, this is what a histogram looks like of this particular image. So as you can clearly see, with the help of histogram, you're able to capture what are the most highly frequent pixel values that are there in the image. So, I mean, this is interesting. Why? Because then you can quickly see that, okay, not all the values are being covered for this particular image, right? If you look at this, only the majority of the values are like concentrated in these pixel values, somewhere between, I guess, let's say 20 to 110. Those pixel values are being covered. But to have a high contrasting image like the one bottom, you would ideally want your entire histogram to be like a normal uniform distribution, not normal distribution, to be a uniform distribution, such that all of the pixel values are equally covered. Why? When that happens, you can see the contrast between each pixel to pixel. When I say contrast is nothing but the difference between the pixel values. So because of making sure that all the pixel values are possible, are having high repetitive frequencies appearing in the image, so the nearby pixels will be of different values. So then you see a contrast when you're going from one pixel to the other pixel. So for example, if you zoom in at this patch, okay, so if I'm going from left side to right side, I see I'm going from a lighter color pixel value to a darker color pixel value. So this is a jump, right? I mean, not jump. This is a shift, which is a strong shift. So we usually call it a contrast. So this is what contrast means. It's like a sudden shift in your movement or path of the images. So With the help of histogram equalization, we convert the original histogram, which is the top one. Sorry, we convert this original histogram to have a more uniform distribution, which is shown on the bottom. Now, with the help of this uniform distribution, you're making sure most of the pixel values are having some better non-zero frequencies, such that the final image will have contrasting values. So I hope this is clear. Any doubts in the idea of histogram? What is a histogram? What is histogram equalization? What is contrast of an image? So enhance usually means contrast. You're improving the image quality, and in this case, since it's contrasting is one way to improve the image quality. That's why we are saying it enhances the image. It can mean many things. Usually, image quality can be enhanced with a lot of things, not just contrasting. But in this particular case, contrasting helps basically. Any doubts in the understanding of this mechanism? Great. So if there are no doubts, let's go to the second image and see why that is not uh, happening. So like I said, we try to make the histogram uniform. Original histogram, we try to make it uniform, but there is obviously certain limitations. You can't always make it uniform all the time, because it actually depends on how your original distribution, histogram distribution, is also like. In this case, it is pretty much a decent histogram distribution. That's why we are able to convert to uniform. But in images like this, on the top image, if you look at the histogram, it is just one peak, because most of the values are zero. So it is just one peak at the start, and remaining all have very small, almost close to zero values. In those cases, it's really hard to do histogram equalization. You will end up with something, a blurred image like this. You will not enhance it. You will, in fact, make it even worse. You can make it like kind of like, because what we're trying to do, we're trying to make all of them have equal colors, right? So we're making, since previously there was no white at all, now you want white to come inside. That is what histogram equalization is doing. Now, in the process of making white come, it is kind of it's kind of making the image quality bad. It's making this entire white fog of sorts on top of the original image. So that is why image histogram equalization does not always work. It depends on what is the input histogram distribution also like. So you should be careful when histogram equalization works, when it doesn't work. So to understand it better, this is the actual formula for histogram equalization. So you take the PDF first and you calculate the CDF, which is cumulative distribution function. So for people who are familiar with it, let me just show you next. Yeah, this is the CDF. So CDF is nothing but the you sum up the probabilities of all the values before that particular x value. So if I have a probability histogram, right? Previously we saw the histogram. If I want to calculate the CDF of that histogram, we calculate at every point, like CDF at 0, CDF at 1, CDF at now CDF at, let's say, any point, let's say 2. CDF of 2 is nothing but the sum of probabilities of all the values before and equal to 2. So if let me write it down. So CDF of 2 is nothing but probability of 0 plus probability of 1 plus probability of, okay. So this is what the CDF of 0 is, or CDF of 2 is. You keep on doing it for every value, and you typically end up with something like this. So I hope this is clear. That is what this formula also is saying previously. The summation is coming from there. Okay. Now let's move ahead and see. Let's talk about computational complexity. So it's actually not a question per se. I'll explain it, how this will be helpful. More than a question, I think it's more of a concept. So let's first understand computational complexity of performing this 2D linear filter on this image. So let's say I have, let's call this the original image. Let's call this image I. Let's call this filter is actually, let's call it B. Okay. If I'm performing any patch operator, doesn't matter if it's convolution, correlation, whatever it is, perform any operation, patch operation, there will be some amount of computational complexity that happens, right? Okay, maybe you guys can take a guess, since we want to keep it interactive. Take a guess what will be the computational complexity. So what is computational complexity? It is nothing but the number of operations. Number of operations. Now, what is the operations that happen in our particular patch operator? That is number of multiplications. That is a major operation, right? Okay. So basically calculate the number of multiplications when you have this filter B, which is having a patch operator done on top of image I. Any guesses what will be the computational complexity? Take a guess. I'll just wait for a minute. As Bharatan has pointed out, it is true. Maybe let me generalize it uh, and show you the formula itself. Okay. So, like I said, typically what do we do in the linear operators? We have your input I image, we have this filter, we place this filter on top of it, and then we calculate an output, and we keep on repeating this process. Inherently, what we're doing, we're multiplying, right? That is what I said. We basically multiply with each element over there, and we sum up all these multiplications. So, if you look at this multiplications, we are basically multiplying each element of the filter with each element of the image patch. Sorry. So, for one particular use case, for this particular operation, okay. Now, this particular operation is nothing but 1 comma 0. So, this f will be 1, this will be 0. You keep on basically doing for every patch. So, you're basically multiplying how many of this is cross 3, and this will be a 5 cross 5 image. So, you keep on multiplying input image, whatever is the input size, and whatever is the filter size, that many multiplications usually happen. So if you want to generalize it, this is what at each pixel x comma y, there will be m cross m multiplications. This m is nothing but the filter size. This is nothing but filter size. And totally how many pixels will be there? That is the size of the image itself. So total what do you have? M square into n square. So previously we had 5 cross 5, 3 cross 3. That's why we had 25 into 9. Now the idea question is maybe again you anyone can answer. Can we do this efficiently? If yes, how can we do this efficiently? We actually solved this efficiency problem in one of the questions in today's session only. Just try to connect with what all we solved today. Can we make this operation, whatever we saw, which has like m square into n square multiplications, can we make this more efficient? Any guesses? What do you think? Is it possible? Okay, FFT. But using FFT, doing the same calculations again, converting it into FFT is a computationally complex process, right? I'm thinking, just think of in the terms of these operations, what we're doing. We're simply doing multiplication, right, over here at the end of the multiplication and addition. Can we make this efficient using the same multiplication addition operations? Let's not complicate and go into FFT. Convolution is the operation name. So right now, that is what convolution. It means any operation. Here we are irrespective of whatever operation is happening. I'm not saying operation wise efficiency. I'm saying if even if you're doing convolution, you will do it in similar way, right? You will do the same multiplication of fij into I of those particular patch values. Convolution is also doing the same way. My question was this process of multiplication, it is costing us a lot. Can we do it a better way? So maybe let me quickly show you. Answer is yes. And we can do using separable filtering. So this is where you remember we had a question in the one of the initial uh, slides where I asked if K is a separable filter or matrix or not. So here is where separability is helpful. Let's see why. So these are some standard filters. What you're seeing, the names are also written below. So this is called box filter, bilinear filter, Gaussian filter, Sobel filter, and corner filter. All of them are used for different things. Like for example, Gaussian is used to blur an image, like smoothen an image, kind of a thing. Whereas Sobel is used to detect edges in an image. I will explain that in a few minutes. But think of these, all of them are like standard filters which are existing. But even if you're getting confused, think of them as simple matrices, and these are the matrices which you see. Okay. Now, previously, what we did, we took that we used to take any image. We used to keep this matrix. This is a filter, right? Let me just write it. So this will be a filter. So we have this original image I. We place this f on top of I, and we do operations. So here, what we're doing, we're placing this entire 2D filter on top of this 2D image, and we're doing this movement, like moving one column at a time, one row at a time. But what if instead of placing an entire 2D, can we place a smaller representation of this filter? Answer is yes. This particular vector is one component of this particular filter, and instead of placing an entire two-dimensional filter, maybe let me write it in some color. You can actually just place this vector, which is one dimensional. The image remains the same. So now immediately the operations are reduced by half, right? Previously we used to do how many? Here we did m square. Here we are just doing m. But of course you'll argue, anyone will argue, but here you're only just using one component of that matrix. There is another component which is missing. How do we do that? Not a problem. We'll just add it with the vertical one-dimensional component of this, and this will be m. Now the answer will still be less. It will be just 2m. 2m is much less compared to m square. So maybe I'll take a step back. Let me go even slower. First, let's see what is these components that are coming from. Let's call this matrix K. Previously we did. What did I say? K can be represented using those SVD decomposition, right? What was the decomposition? Sigma, like summation of I from sigma I ui vi transpose. This is what the separability told us. Now I said that ui and vi are vectors. Okay. It so happens that all of these filters which you have, which are standard filters, these all are separable. So here, this particular one is u. Okay. Similarly, v can also be written like this. Vi is nothing but the transpose version of it. 1, 4, 6, 4, 1. So if I want to build k again, k is nothing but ui into vi transpose. This is vi transpose basically. So it's nothing but this outer product between this row 1, 4, 6, 4, 1 into 1, 4, 6, 4, 1. Okay. So what will be the final matrix since these are 5, right? So this is 1 cross 5, and this will be 5 cross 1. Sorry, my bad. It should actually be the opposite way. One, 4, 6, 4, 1, 5 cross 1. This will be 1, 4, 6, 4, 1. Now with this outer product, we will get a matrix of 5 cross 5. Okay. And then if you do this if you actually do this outer product, you'll end up with this original matrix, which is this matrix. Maybe I'll just write it down over here. So if you do this outer product, you'll end up with this. That's an exercise you can all do. So the outer product of these simple row vector and column vector will give us the original matrix. And that is what we're taking advantage of. And we are saying ki, instead of using the entire 2D matrix at a time for calculation, we can do separately one dimensional horizontal, one dimensional vertical, and you add them up and you get the values. So if you look at it, this is what the calculation looks like. So previously, what we had previously, we did something like this. So for each pixel, we have m cross m multiplications, and there are total n cross n pixels. Now, if you use separable Gaussians, just like in the previous example, only the same thing, we'll still have 2m and n cross. Here we only have 2m because we are doing 1D separately and plus another 1D separately. And each 1D will act upon this 2m. So you'll have 2m n cross n square basically. I hope this is clear. I don't think you'll end up with that, Bharathan. It's the same equations which I'm showing you. And how you got 25 into 9? You got 25 into 9 by multiplying 5 into, sorry, by multiplying 3 into 3 into 5 into 5. The same way here, if you break that matrix, you'll have much smaller. You'll have just 2m over here and you'll have these values. Basically, you'll have 6 into 5 into 5. You can just try it out once again. And if you have any questions, we can discuss tomorrow, next week. Any other doubts? Anyone else? Anything regarding this separability and all? So this all goes back to the formula which we saw, SVD formula. So this is just a way of doing efficient computations. This is in fact built on top of this. I think back in 2018, 2019. In fact, even nowadays also, people use separable, depth-wise separable convolutions and everything in neural networks basically, which are very popular. So this is, if you understand this concept, right, it will be very helpful to understand a lot of state of the art neural networks which actually use these type of simple decomposition of matrices, so that they can actually deploy these models in real time and achieve higher inference and everything. Any doubts at all? Okay, great. So if there are no questions, let me go ahead. So this is an example of that same 2D Gaussian. If you want to blur the image, you can either do completely use a 2D image and blur it, or you can do step by step. You do first do horizontal, and based on that output, you do vertical, or you can do first vertical and then on top of it you do horizontal. Either way works. It will give you the similar same output as you will do the entire 2D Gaussian blurring. Okay, coming to the final question. So here we have intensity images of different frequencies. What will be the frequency images? Maybe you can tell me in terms of like dots or something, like in the frequency image map, right? How many dots will be there, and will the dots be closer to origin or far away from the origin? You can just mention such type of sentences and you can put it in the chat. The I think has Bharatan has pointed out that is correct. Maybe I'll explain it also. It's actually two dots. Not, I mean, if you're considering the origin also, otherwise it'll be just two dots, which is the actual frequencies. Origin frequencies are not matter. So here, what is happening in the, let's look at. So these are called as intensity images, which are on the top. Let me write it down. What we see on the top, we can call it as intensity images. What we see on the bottom, we call it the frequency images. So you can basically represent any image which is in pixel form, which can also be explained, which can also be represented using FFT in the frequency domain. So that is where one representation of images come from. How you go from images from pixel domain to images from in frequency domain with the help of fast Fourier transform, and that is very well clearly explained in the lecture videos also. But there is a slightly detailed proof of how it exactly happens. But all you have to understand is you can represent images from pixel domain into its corresponding frequency images with the help of fast Fourier transform. Now, what is that frequency talk about. So any repeating pattern, like for example, in intensity, like which we usually see, which is the top, right, which is the pixels which we see. Now let's say there is a change between pixel to pixel. Like in the first image, if you focus, there is a change. You see white, then black, then white, then black, then white. There's like a constant change, and this is repeating itself a lot. And this change is also in a certain way. It is always happening. Like the black and whites alternating are similar in nature. So this particular change of pixels, that is what is capturing the frequency, and that is what can be represented in frequency images. So this is one intuition to understand how we are going from pixels to frequencies. So if you let's say have a image of sharp edges or anything, anything noisy or sharp edges, those usually will have high frequencies because the shift between side by side pixels is high. So because of that, the frequencies will be high. Whereas if you have images with a lot of smooth brightness kind of a sort, you the shift will be very small, right? Because it's more or less smooth. And since the shift will be pretty small, yeah, I think the frequencies will also not be high. The frequency will be closer. Now, how in the frequency images, this is usually the origin, or you can also keep it vertical also. So the closer the values are to the frequency, to the origin, the frequency is smaller. The farther you move away from the origin, so if you're going up or you're going down, it's also symmetric. Okay, that you need to remember. If you go here, left or right, you have more and more frequency in that particular direction. So let's, with that in context, let's look at the first particular image. Um, you have the intensity changes which you are seeing, right, black and white, but they're not very drastic or very noisy or very sharp. They are there but not that sharp or not that noisy. So that is why you have frequencies which are closer. So this is all relative over here. We don't have exact values. Since we have a bunch of examples, it's all about relative frequency, relative distance between the dots. That is what we are representing. Now similarly, if you have f is equal to 5, you have the shifts happening much more faster than the previous f is equal to 4. That's why you have higher frequencies. So the dots slightly go up. If you come to the extreme case of f is equal to 10, so the shifts happening much faster. Now because of that, it means that the frequency is very high. Now the dots are much farther away from the origin compared to the previous ones. So this is how you typically correlate intensity images to frequency images. Any questions, any doubts? You can always, again, like I'm constantly saying, please look back into the lecture videos. They're very helpful to understand the tutorial videos, because if you come without watching the lecture videos, it'll again be harder for you to understand what problems I'm solving. So please look back into the tutorial videos in the entire week, and every Tuesday we solve the live sessions. We solve the problems related to those videos. Okay, coming back to this question, any doubts, anything that's not clear? Great. So then let's go ahead to the coding part of today's live session. So since this is the first, sorry, so yeah, this is the first live session for this particular course. I will start with the very basics of NumPy library, which is used in Python. Even before going to that, I'll even begin with even simpler of what is this notebook which you see, this browser which you're seeing on my screen, right? What is it helpful for, and what is this language Python? I'm pretty sure, I think at this point of time everyone knows what Python is. Still, I'll give you a basic introduction, and then we can go into using what is this NumPy library inside Python, why is it helpful, and we'll also see some examples of what all you can do with this library. And lastly, we will end with how you can, because it's all about computer vision, right, this course. So how you can use certain libraries in Python to load the images, to manipulate the images. Like if you want to rotate the image, you want to shift the image, you want to flip the image, how all you can do that using Python language. Okay. Again, just like the slides, at any point of time, if any code or any concept is not clear, please stop me and I'll explain myself. And I'll share these collab also. It will be very helpful if you guys can go through these collabs as and when we are sharing. in that 1 week time, so that by the next week we'll have the code wise also the complexity keeps on increasing every lecture. So it's better to have your basics cleared in the first few weeks as soon as possible. Yeah. So coming to the first important thing, Collab Notebook, which is nothing but this particular browser which I opened. So Google basically has this product called Google Colab, where they provide GPUs and a lot of CPUs for free if you have a Google account. Of course, there are certain limitations into what type of GPUs you can get, what type of CPUs you can get, because it depends on what level of membership you have with this particular product. But why do we need GPUs before even going to what type of GPUs is? So the idea of using GPUs is to make all of your neural network algorithms or any AI, modern AI algorithm to run or train faster. You need these GPUs. How does it do it faster? Don't worry, we will look at it when we are coding the neural network itself. That I'll explain it back then. But just have an idea that GPUs are needed so that you can train your AI, modern AI models much faster. CPU, to simply compare, a typical CPU would take around probably, let's say, 20 to 30 days to train the same model, which a GPU would take around 2 to 3 hours. So that is the impact of using a GPU. So always remember, whenever if you're ever working on these any modern neural network architectures, you always need to first procure a corresponding whatever GPU for whatever use case you have. You don't have to go with the most costliest GPU, because depending on your model, depending on your use case, you can always use smaller and smaller GPUs also, but always use a GPU. That is the point. So yeah, now coming to Collab. So Collab basically, since not everyone can afford GPUs, Collab basically gives out free GPUs to people. If you pay slightly higher price for your membership, you can get better quality GPUs for your work for your code basically. So typically, you first create a Google account. I think everyone has one. If you don't, please create a Google account. You go to google.com, you search for Google Colab, and then it'll ask you, it'll open this particular, it'll open something like this. If you It will ask whether to open a new notebook in Drive, open notebook, upload notebook, etc. You'll have a bunch of options. I will share this collab notebook. You can always say upload notebook and upload this notebook which I'm providing. Why do we call this notebook? Now, that is a second question. So, what is the difference between this type of writing code, like where I have some text with me, I'm explaining some text, and then I have the code itself also? Whereas you must have typically written codes in what is editors, right? Like Studio Editor or any other Notepad plus plus editor. All of these are editors where you write code. Usually, you write it in terms of script, where you have one Python file or any C plus plus or file. You write all the import statements, your algorithm functionality, and you write your main function and everything, and you run that function using your command line or the terminal in your editor itself. So those are called as usually script functions, and these are usually called as notebooks. These are called notebooks because you can write the text or images along with your particular code blocks. So you don't have to execute whenever you want to check small code functionalities in your entire big file. You don't have to run the entire file to check that particular functionalities. You can always create something called as these code blocks. So for example, I have these 3 lines of code. Now I want to just check if these 3 lines are working. I can do that with the help of notebook. I can just press run over here, which you see this play button. I just press this and only these 3 lines will get executed. Nothing else will get executed. So with the help of notebooks, you can check very quickly a particular chunk of your code instead of running the entire code at a time. So very helpful when you're initially learning about new languages, or very helpful when you're trying to debug your code, etc. Okay. I think that is enough about notebooks and collabs. Now coming back to Python itself. So Python is another modern day programming language. Everyone must be aware of C. So C is one of the fundamental foundational language which most of you all must know. Python is a much more advanced version, which is different, slightly different from how C is written, but it the way it operates is pretty much similar. You import certain statements just like you import certain libraries in C, you import certain libraries in Python. You declare some variables just like you declare variables in C, you declare variables over here. And you also have certain arrays which you declare in C. Also, you have C arrays, right? Same standard even in Python. You have something called as NumPy arrays, or there are some other data structures also like list and everything. But the advantage of Python comes because of its OOPS functionality. OOPS is like object oriented programming functionality, and other type of speed ups and everything. Much more user friendly writing and all. So that is other differences between Python and C. I won't go in deep over there. So that being clear, maybe let's jump into what this NumPy library itself is. So like you can see on my screen, NumPy is one particular library that is used in Python to create multi-dimensional, high-performance arrays. The same arrays which you create in C, you create in Python using NumPys. But the advantage over here is you can do much more sophisticated calculations, like all those linear algebra, right? The SVD decomposition, calculating the singular values. All of them can be done very simply using 1-2 lines with NumPy. And you can also do matrix multiplication. You can do basically a lot of scientific computations, scientific calculations. All of them can be done using NumPy arrays. So there are very specific functions inside this library using which you can do those calculations. So that is the best advantage you can say of using NumPy arrays in Python. You can always go through exactly line by line whatever is mentioned over here, but I'll just go ahead for now. So first, typically you need to install NumPy. Again, if you're using Colab, you don't have to worry about installations and all because Colab is on your browser and the actual machine on which you're running is somewhere in Google's data center. It is it has no relation to whatever laptop you have. That is again a best advantage of using Colab is it is kind of like your local machine agnostic. Doesn't matter what local machine you have as long as you have a good internet connection and you have a Google account, you can work with Colab from anywhere you want. All the GPUs, all the CPUs, everything will be in Google's data centers. You don't have to worry about. And typically, these machines will already have most of the basic libraries installed. But just in case, sometimes if it's not installed, you can install it using this command called pip install. And what this NumPy is the library name. You can give whatever library you want to install. So once you do this, most likely NumPy is already installed, but even if it's not, you can use this command to install it. Now, once you install, you need to first import this particular library before doing anything with that library. Now, how do you do that? That is where you create this import statement, which I'm highlighting. Import NumPy as NP. So the idea of having these shorthands NP is basically you, it's ease of coding. You can always do just write import numpy, it'll work perfectly fine. But when you're writing longer codes, right, it's hard to always write numpy dot whatever, like numpy dot this, numpy dot that. Writing the entire word numpy is hard. So usually people prefer some shorthand notation. That is where this np comes in. So you write import numpy. How do I want to import it as np? That is what the statement means. So I'm going very slow. Bear with me since it's the first session. For people who are already familiar, great. But people who are not, please ask more and more questions of anything that is not clear. Please don't hesitate. So that is where you first import NumPy. Now, the most fundamental unit of any NumPy library is NumPy arrays. Without NumPy arrays, you can't do anything. You need to create a NumPy array to use NumPy library. That is the bare minimum. That is the minimum. That is the bare minimum. So how do you create? You can either create from Python list. A list is nothing but this particular value which you see, right? In square brackets, you have 1, 2, 3, 4. So this is one type of structure which is present in Python, which we call it as a list. So in using this particular type of a structure of this square brackets 1, 2, 3, 4, you can create an NumPy array. How do you create? You just write np.array and you give input this particular list. Now this will create a array which is stored in this variable arr1d. You can give any name as long always it's a good rule of coding. Give variable names which makes sense to what it is doing. Don't give random xyz because it will be hard for you to understand what is that variable doing. Always give sensible variable names. Why did I give arr1d? Because it's a one-dimensional vector, right? If you think about it. So 1, 2, 3, 4 is just one-dimensional vector. Now, if I want to create a matrix, it will be something like this in the next line, where First column has in first row the two columns are 1 comma 2. In the second row the two columns are 3 comma 4. So it's a 2 cross 2 matrix. So that's why I name it as ARR2D. And again, to create the array from this particular list the same way, np.array. You can also create from tuple. So tuple is just like a list, but slightly there is variation to that structure also. In the way you write it, you can quickly see tuple uses parenthesis, this curved brackets, parenthesis, whereas list uses square brackets. So that is notation wise difference between tuple and list. Functionality also, there are subtle differences between how you can use a list and tuple. But for your NumPy array, it doesn't matter. You can always create a array from a tuple or a list just the same way as you created previously, np.array, and you give that input. Okay, great. Now once you create a NumPy array, now what can you do with it? These are some basic functions you can use with NumPy array. Now, firstly, okay, before even going to, oh, sorry, my bad. So this is one way of creating NumPy arrays. Another way is using these functions, built-in functions, which you have these 6 7 functions. Using these built-in functions also, you can create different arrays. Let's go step by step. Let's say if you want to create an array which is starting from 5 and which ends at 15, but it should have values after every in the step of 2. Like you have 5, you have 7, then you have 9, you have 11, you have 13, you have 15. So if you want to create a NumPy array of that, you can use this particular function np.arrange, and it will and you can mention what is the start value, what is the end value, what should be the step value. So you can quickly see the powerfulness over here. Now, ideally, if you wanted to create a array like this in C, or even in Python, if you want to create a list like this without using NumPy, you would have to write a for loop. Inside that for loop, you would basically keep that condition that it is skipping two things, and then you're storing those values. So small 2 3 lines of code. But here, with the help of this np.arrange, it's just one line, and you get everything what you will get in the for loop. Honestly, in the backend, that for loop is itself running, but you don't have to worry about it. That is the beauty, or that is the powerfulness of NumPy. It'll take care of all the backend unnecessary details which the user should not be concerned. Okay, that is one way. Now, if let's say you want to create more equally spaced, like you don't know what number of steps you want to take, but you know that I want a certain number of points between a particular range. Like I want 5 values between 0 to 1. So you basically use linspace, where you give the initial value, final value, and how many points you want from these. So it will automatically divide equally. So it will take 0, 1 by 5, 1 by 5, 1 by 5, 1 by 5. Like that, it will take 5 values and give those 5 values. Now let's say for certain cases you want to create a array with nothing but 0 values. Okay, that is a very important use case. You will see in later lectures where you'll use such arrays. So for that case, what you do np.zeros. It basically says create a array with all 0 values. What should be the size of this? You can give whatever size you want. 2 comma 3, it'll create 2 rows, 3 columns. You can give whatever 2, 3, 4, 5. It'll give 2 rows, 3 columns, 4 channels, and fifth is the fourth dimension. So you can use whatever size of array you want to create, but you have to understand that whatever you create, all of them will have only 0 values. Similarly, np.ones, here also you basically create you create an array with all the values as 1. And now this is called as np.I. I is nothing but identity matrix. I'm assuming everyone is familiar with identity matrix, where you have diagonal values as 1, all the non-diagonal values will be 0. That is an identity matrix. An identity matrix are usually square matrix, so that's why you just mention one number. It automatically assumes the column to also be that particular number because it's a square matrix. Now, similarly, if you want to create an array filled with a particular type of a number. Previously, we had filled with zeros, filled with ones. But let's say you want to fill it with some random number. So that is where this np.full comes in. So you mention what should be the size here. Let's say 2 comma 2. Then you have the value itself. What should be the value that it is filled with? Here you're mentioning 7. Now let's visualize all these. You use the standard print statement and you print each of these variables. And this is what we'll see. First one was arranging at the spacing of 2, 5, 7, 9, 11, 13. Second one was picking 5 points between 0 to 1. Third is all zeros. Fourth is all ones. Fifth is an identity matrix. And last one was all elements with the same value, which was 7. Now let's look at what are the attributes. Before that, any questions? Anything that's not clear about what is an array, what, how to create an array? Any doubts or anything? Okay, then let's move ahead. Now let's come something called as attributes of an array. So every array has certain attributes are like features. If you want to define an array, you need these features to define an array. What are these? These are the typical 4 features you can say are attributes. First is the shape. Just like how I said, right? The matrix also has a dimension, right? Like m cross n, whatever dimension. That is nothing but the shape over here. It returns basically saying what is the dimension of the array, an numpy array. Whether like basically in the same format of m cross n cross. If you have more than 2, it will be k. If you have more than 3, it will be whatever other dimensions. Then comes d type. So typically, if you all wrote codes in C, you know that you have certain data types present in C, right? Like you can define a variable as an integer, you can define a variable as a boolean, yes, or true or false. You can define a variable as a string, like ABCD, any string. You can define a variable as a float, which is decimal. Same thing here also, you have a bunch of options. You have the D type is nothing but the data type. It could either be an int 64, float 32, or a complex 128. So these 64, 32, 128. Okay, maybe let's keep it more interactive. Any guesses what are these numbers 64, 32, 128? Just post your guesses in the chat. What do you think these, when I say int 64, what does 64 mean? When I say float 32, what does 32 mean? When I say complex 128, what does that 128 mean? Yes, correct. I think everyone knows that. So it's basically the number of bits representations. And then comes the number of dimensions that are there. So there's a difference between the dimension value itself and the number of dimensions. Like for example, a matrix, if I use ndim of for that matrix, it will give me 2 because it has 2 dimensions. But what is the values of each of these dimensions in those 2 dimensions? That you'll get from shape. So there is a difference between shape and n dimensions. Ndim is the short form from n dimensions. Then comes size. So size is again different from shape because size says number of elements. So it's nothing but like a multiplication of the two values of shape. Not just two, like whatever values are there in the shape, multiply all of them, you'll get the size. So these are typically the main attributes of NumPy. That is what we do over here. We first create 3 NumPys of 1 dimensional, 2 dimensional, 3 dimensional. You print all of their attributes. So let's see the attributes itself. 1D shape has 4 comma nothing. So D type is in 64, only 1 dimension, size is 4. For 2D it has shape 2 comma 2, D type again in 64, 2 comma 4. For 3D it has 2, 2, 2, 64, 3 and 8. Okay. Now let's go ahead. Now next important thing to understand an array is, fine, you created an array, you understood what are the different attributes, but how do we pick some elements in these array and perform certain calculations or operations? So how do we pick? There are two different ways to pick. One is called the indexing, or other one is slicing. Let's first call indexing. Indexing is if you want to pick a particular element from a particular position in that array. Like for example, in a 1D vector, if I want to pick from a position of 2, I will give the value as 2 and I'll get, so if I want to pick a position from 2, actually I should give a value of 1. So why am I doing that? Because in computer science, you always start indexing from 0, and in mathematics, you always start indexing from 1. So if someone asks you want element of position 2, so ideally you should give the index value to be 1. So how do we do that indexing? This is what we can see over here. So you create an array of 1D, okay, and then this square bracket inside that number which you're giving, that is the position index value which you're giving. So 0 if you're giving, that is the first in position value you're taking. 2, it means a third, since you're starting from 0, right? 0, 1, 2, which is a third position. So array 1D of 0 gives you 10, array 1D of 2 gives you 30. Similarly, if you want to index from a 2D also, you have to specify the exact uh, value. Like since it's 2, you have to specify both the row and the column. Now you can quickly imagine if it's 3, you'll have to mention 3, and if it's n dimensions, you'll have to have n values. So it kind of gets tiring over there. But yeah, if you have 0 comma 1, it means the first row, that is 0, and the second column. Similarly, 1 comma 0 will be second row, first column. Now comes slicing. Slicing is when you want to pick a chunk of values, not just one value. So that is where slicing comes into play. So if you see, if I want to pick value starting from position, second position, that is by 1, to the final fourth position, which is 3. But this last 3 will not be included. Okay, remember that. You'll only include the first one will be included. So first 1, 2, that's it. 3 will not be included. So the other number after the colon will not get included. That is one notation which you have to remember. Similarly, if you don't want to mention, if you want to pick all the columns in this two dimensional, I'm picking the first row. Column I have no restriction. I want all the column values. You just put the colon. It will pick all the column values. Similarly, if you want to pick all the rows for that particular column, you just put colon, and it will pick all the rows. So yeah, so this is again, please practice more and more. You could try with a bunch of bigger arrays, matrices, tensors, and everything, so that you'll get better, understanding of how these things are working. Just by going through today's course or lecture won't help you. You should actually start coding. Then only you'll understand how to do all of this. Another is stride, which is again, you can provide an optional parameter in the slice itself to specify what should be the step size between elements to elements. So if I provide like double colon 2, it means pick every other element. So you, the same way like step size was used, right, in dot arrange. In a similar way, you use a slice step size when you're slicing also. Now you can also use Boolean indexing, just like if let's say you want to pick only those elements for which the values are certain, higher greater than certain other value threshold. Like in this condition, if you see array 1D greater than 25. Now if you write this particular array 1D greater than 25, what it creates is it creates an array of true or false values. Wherever it is greater than 25, it creates true. Wherever it is less than 25, it creates false. Now, when you're sending that array as an indexing in the outer array 1D, then only those true values will get picked. The false values will not get picked. So in your case, in this case, it will pick only 30 and 40. So I hope this Boolean indexing is clear. So if it's not, let me repeat quickly. Array, first, inner thing, what it is doing when you say array 1D greater than 25, it will create an array where each position will have either a true or a false with it based on this condition. Now that array is going as an input to the outer array 1D square brackets. Now wherever it is true, only that will get picked and printed. Others will get ignored. You can always print this condition, right? Intermediate condition, and see what is happening for your better understanding. Yeah. So there is another way to indexing, where you already know what indices you want. It's not like you just want one. You want like 10 values, but you know what all those 10 positions are. So you can mention it. You create another array called indices. You specify all the position values in this indices array, and you give this as an input to the original array. So now now you're selecting only those values which are at this position. Yeah. Any doubts or anything? I know I might be going a little bit fast for people who haven't worked with NumPys. It's just to give you an overview idea. Please try again. I'm happy to answer any questions in next week's class. So maybe we can do this next week for the first 10 minutes or something. You can come back with questions based on the code or anything, and I'll discuss that in the next week's first 10 to 15 minutes. So let me come to what all operations you can do with NumPy. So the first operation we can do basic operations, arithmetic operations, addition, subtraction, multiplication, division, exponents. How do we do that? Just like how we write in mathematics, just write array 1 plus array 2. It will do one. It will do element wise addition. It will do 1 plus 4, 2 plus 5, 3 plus 6. Subtraction also, array 1, array 2 will do that. Even array 1 This asterisk is this particular symbol, multiplication symbol. Sorry, this particular multiplication symbol into array 2. This will again do element wise multiplication. Division also same, element wise. Exponent also element wise. That is what the basic operations. Now, let's come to some universal functions. Like I said, NumPy is majorly helpful for these more standard operations, not the basic ones. So let's say I want to create a sign of a function. Now, the sign of a function, you you want to create, you want the output from a sign function, not create sign of function. No, you want to output from a sign function. So you have a bunch of angle values like 0, np.pi. So you already don't have to create what the pi variable is. It's already there in NumPy that you can access it by using np.pi. So that is the pi value over here. Divide by 2. So this will be pi by 2, which is nothing but 92 degrees, right? Similarly, np.pi, which is just pi, which is nothing but 180 degrees. So by using the function np.sign, you send the array which has these three values, and the output you get 0, 1, 0. Similarly, for cos also you send the same values and you get similar outputs. You get 1, it's actually 0, and then you get -1. Can someone explain why we actually didn't get 0 over here when we got this value? Any guesses? Ideally, we all know that cos 90 is 0, right? But why didn't we get 0? Maybe you guys can also think about it and let me know in the next week. Very simple. It has nothing to do with the course or anything. It's just for your personal knowledge. Just look at it in your own time. Similarly, you can also use exponential functions. np.exp is nothing but that e to the power x, right? That function. So that is what np.exp is. And you give a bunch of values, e to the power 1, e to the power 2, e to the power 3. Similarly, you have logarithm functions, log of values, whatever you want, log 1, log 2, log 3. Now, you can also have absolute values. Absolute is modulus function, where you output is only non-zero values. Output is only positive values, non-negative values. I mean, output is only non-negative values. So here, if you give a function, if you give values like 1.2 minus 2.80, the answer from absolute will be 1.5, 2.8, and 0. Negative will become positive. Square root again, it'll square root of a function, which basically takes input only positive values. So that's why we give np dot square root. For that, the input should be np dot absolute. Convert all negative to positives, and then you give that as an input. Now let's move ahead into something called as array broadcast. This is a very important concept. You will definitely get questions for your assignments on this, most likely. Let's understand what this broadcasting does. So typically, when you have these lot of arrays, right? Most of the times, arrays might be of different shapes. When I mean shapes, different dimension values, right? It can be 2 comma 3, one can be 3 comma 3, or etc. Now you want to do all these operations like addition, subtraction. Sometimes these operations are very dimension dependent. Like for example, if I want to do addition between two arrays, but one array is of two dimensions, one array is of one dimension, then you really can't do addition in that case, right? How do we take care of those situations? That is where broadcasting helps. So if you don't do if you're not doing broadcasting, what is the other way? You manually check the dimensions for these two arrays, and then you duplicate the values of the lower dimensions, whichever is not whichever is smaller than the other array. You duplicate the smaller ones to have the same dimension as the bigger one, then you add it. So the same operation is what broadcasting does for you in a much more smarter way, so that the user doesn't have to manually go and verify what are the different dimensions of the arrays and everything. Let's look at it with this example. So let's say I have an array of shape 3. It's a one dimensional array. 1, 2, 3. That's the shape. That's it. Now if I have another array of shape 3, comma 1, okay, where it is 4, 5, 6. Ideally, these are not the same entities. If you look at it, the first one is one dimensional, the second one is two dimensional. Two dimensional because it has three rows, one column. First one is just one dimensional, just three. So we would want this to actually duplicate into 3 comma 1 and then add. That is what we ideally want. But NumPy does something inbuilt. You don't have to worry or write anything. If you just add array 1 plus array 2, it will automatically first convert the first array 3 into 3 comma 1 and then does the element wise addition. So that is what it is happening over here. Similarly, for the next case also, if you have 2 comma 2 and just 2, automatically the second array duplicates itself into 2 comma 2 and then it adds element wise. Otherwise, ideally, that doesn't make sense to add a vector or one dimensional entity to a two dimensional entity. It means nothing unless you duplicate. So remember that you have to make sure the broadcasting needs to happen properly. Now, how can broadcasting happen always, or are there limitations? Of course, there are limitations. So these are the rules to broadcasting. Maybe in the interest of time, I'll not go into all the rules. Please look into the rules. There are certain fixed rules, very simple rules. It just has to say that the ending dimensions should either be one or it should have nothing so that it will match with the overall other dimension, other arrays dimensions. Because if it is having some other values, like for example, 2 comma 3 and 2 comma 4 can never have what is the broadcasting done because there is no ending dimensions that can match with each other. So those are some rules that are there, just simple three rules. You can just look into it in detail. It is mentioned in this collab. But all I want you to take from this particular section is something called as broadcasting is present, and it is very helpful, which underlying only basically makes the arrays compatible when you do operations. Now let's come to some array manipulation techniques. So first basic array manipulation technique is reshape. So as the name suggests, you have an initial shape of an array, and let's say for some reason you want to reshape it to do some other operations. How do? You do use this function called dot reshape. So you create an array here, arrange 12. What does it do? It creates an element of 1, 2, 3, 4, 12 values, but it's creating a one dimension. Now, if you want to reshape it into a two dimensions, you can just write dot reshape 3 comma 4. So it takes the original one dimension uh, vector, which is of value 12, and reshapes into two dimensional matrix of values 3 comma 4. So you quickly realize reshaping also has its limitations. You can't reshape 12 into 5 comma 5 because it is not possible. You don't have 25 elements to go from uh, uh, you can't go from 12 elements to 25 elements, right? It's not possible. So always make sure reshaping is possible as long as what you're converting and reshaping into a newer dimension is possible from the same number of elements as the original dimension. Now next, if you want to flatten something, so flatten is basically when you have any bigger dimension array and you want to flatten and make it into a one dimension. That is what flatten is usually used for. So here, it's see, originally we had this new array which is of the shape 3 comma 4. If I use flatten, it will basically give a one dimensional. So it there is something called as ravel. Ravel basically again it it's a very similar thing to what flatten does in a slightly different ways. Basically, one keeps a copy of your original array, one does not keep a copy of an original array, but pretty much the use case wise it remains the same. Memory management wise it is slightly different. Now let's come to the next function. I'm just quickly again brushing into all the major important functions. Please look at it in your own time in detail. So transpose is another function, like the typical matrix transpose, right, where you interchange rows and columns. That's what is happening here also. Let's say you have this matrix 1, 2, 3, 4. You want to transpose it, so now it will become 1, 3, 2, 4. That is what you see in the bottom. Or you can swap the axis. Transpose is limited usually by like the typical transpose, all the columns and rows get interchanged. But if you know for sure what you want to swap, which dimensions you want to swap, that is what you can use the swap axes for. Axis is nothing but dimensions. So that's another term. Axis means dimensions. It's like zero axis means row dimension. Axis equal to 1 means column dimension. Axis equals to 2 means the depth dimension. It's just another word for dimensions. So if let's say I have an array of shape 2 comma 3 comma 4, so you have three dimensions, row is 2, columns are 3, depth is 4. And now if I want to swap the original array 3D, such that the 0 and the second are interchanged. The 2 over here is this third dimension, not the value. Okay, remember 0 and 2 are the axis values. So you're interchanging the first axis with the second axis. So now what happens is actual dimension values 2 and 4 will get interchanged. So now the swapped axis will be of the shape 4 3. I hope this is clear. If you don't, if it's not, please post it in the chat. For now, I'll just move forward. Then we also have concatenations, just like how you concatenate to uh, in normal, what do you say, appending and all, list appending and all you do in Python. That you can also do an arrays, concatenation of two arrays, where you can mention across what dimension or axis you want to concatenate. Like, do you want to concatenate two arrays along the row dimension, or along the column dimension, or along any dimension? There are certain fixed functions also. VStack will always stack vertically. Stack, it will always combine or concatenate horizontally, column wise. Split, if you want to split a big array into multiple, then there is horizontal split where it breaks the column into separate splits. Vertical split where it breaks along the row dimension into certain chunks. These are again existing multiple functions. You also have certain typical elements, typical way to add elements or remove elements. Dot append, you can add the values at the end of the array. Insert is basically, again, if you want to add a particular value at the specific position. Delete is where you can delete the entire values from the array itself. Again, you have some other functions like resize, repeat, and unique. You can just look into it. I'll just go ahead to more complicated arrays now. I'll go into multi-dimensional arrays and I'll stop over here. I think it's almost 9 o'clock. Don't worry, I'll share it and I'll discuss again the same code next week also, where we talk about images with all these arrays which we just created. But for now, let me finish this multi-dimensional array and end the session today. So how do we create multi-dimensional array? Nothing different. What we just did from that time is a smaller version. We can always extend that to a bigger version and create having multiple lists or multiple tuples, or even use built-in functions like zeros and ones having multiple values mentioned. All the operations which we discussed till now are completely applicable even for multi-dimensional arrays. There is no change in that, so don't have to worry about all your indexing, slicing. Similarly, your mat. Okay. Now coming to extra operations which you can do with these multi-dimensional arrays. So first matrix operations is dot product. All of you must be familiar with the standard dot product, where you take element-wise multiplication and addition between two vectors. That is your dot product. Now matrix multiplication is, again, we all must be familiar. It's like you have, let's say A is of dimension m cross n. You expect B to have the same rows as the same number of columns as A. Let's say here it will be n cross k. When you do multiplication between A and B, you'll get m cross k out. It's like performing similar to dot product only, but much more stricter rules you have when you're doing matrix multiplication. Now let's see how the output looks like. So if I have array 1, 2, 3, 4 and 5, 6, 7, 8, these are two arrays A and B. If I'm doing dot product, what does it do? It does multiplication element wise, right? So if you uh, yeah, if you see at the dot product over here, it'll it'll take the first row, and then it dot product between the vectors and the array matrix of the second one. So the same way how you do matrix multiplication, you take the first row of matrix A, and then you multiply it with the first column of column of matrix B. The same way dot product also does. Similarly, matrix multiplication is also the same thing. That's why you get the same values as the output. So I hope that is clear. How we do simple matrix multiplication: we take the first row of matrix A, multiply it with the first row of first column of the matrix B. That is nothing but the dot product itself. So that is what np dot does to matrices, and np matmul also does it. Then we have something called as random number generator, but I'll just quickly finish at this. I think it's already 9. So we want certain functions where we want to generate random numbers. Why is it helpful? You will see in later slides, but it is very helpful because sometimes we want to create certain values for which we just randomly start off and we optimize it during our training process. So that is where these functions, this particular module comes in, numpy.random. Very helpful. It helps in creating a bunch of different random numbers, which can be coming from uniform distribution, Gaussian distribution, other distributions also. So this is rand is one particular function where it generates random floating values between 0 to 1. 0 included, 1 not included. So if you create a single particular value, np.random.rand. If you want to create a particular shape, you mention the shape also. 5 will create 5 different values, each of them randomly sampled from this interval 0 to 1. Similarly, instead of float, if you want an integer random value, you use randint. That's it. You can also mention what should be the range of it also. 1 to 10, it means it will pick any value from 1 to in between 1 to 10. And you can also mention the size, how many such random values you want. If you do rand n, it samples from a Gaussian or a standard normal distribution with mean 0 and standard deviation 1. That is what this particular value is. Okay. Like I said, there are a bunch of other distributions possible: uniform, normal, exponential, binomial, etc. Okay, let me quickly pause then and stop the recording.